Imagine you're baking your grandma's special cake in the kitchen. As you reach for the instructions, you find that they're torn in half. Now this video isn't actually about baking a special cake, it's about cells like yours, which surprisingly go through this every day. Around 10 to 50 times a day, your cell's DNA or baking recipes essentially gets torn apart in what is called a double-strand break due to external elements such as sunlight or toxic chemicals. This can result in faulty recipes which are potentially catastrophic, as double-strand breaks could cause DNA damage that leads to premature cell death, cancer, and mutations. Fortunately, there are two main methods used to repair double-strand breaks: non-homologous end joining and homologous directed repair. If you ever broke a vase while playing in the house, your solution was probably to super glue it back together. This is how non-homologous end joining works. But in the case of DNA, proteins first attach to and trim the edges to make sure that the two broken strands fit back together perfectly before another protein, ligase 4, glues it back together. Just how the vase was never completely fixed, so is our recipe. The proteins don't know if they're restoring the DNA to its original form, so some information could be lost as new bases could be substituted or inserted, and original bases could be deleted. Imagine if we baked a cake at the wrong temperature. It wouldn't taste so good. Worse, we could even burn down the entire house. So to avoid harmful mutations when repairing our recipes, cells with two separate but identical strands of DNA use homologous directed repair. Luckily for us, Grandma always wrote down her recipe multiple times. In homologous directed repair, proteins first trim the edges in a process called resectioning, allowing us to line up the separate strands in what is called a displacement loop. Once they're lined up, we're able to use the complementary strand to fill in the corresponding bases, essentially copying the DNA. Believe it or not, its only use isn't just DNA repair, as CRISPR-Cas9 technologies often leverage these systems in order to accurately manipulate DNA. So life shows us that once again, there are simple machines working both in and around us, and learning how they work allows us to use them as tools that can improve our lives for the better.